Hello and welcome. So in this tutorial we'll learn that how we can create custom solvers for Houdini's Apex animate state, and we will do that using the new sim namespace nodes inside the Apex graph. But before we begin, there are also some prerequisites. I hope you already know that how DOP networks works and how the Apex works, because this is a intermediate tutorial and I won't be teaching you that how the basics of these things work. So now we can switch to Houdini, and before we learn about anything like how we can prototype the solver and create it in the Apex graph, we want to learn that how we will control that solver in the Apex animate state. So first we will drop down a geometry node, and then we will drop down the test geometry Electra, and we will use this test geometry to test our solver on. Now we want to output the Apex character and let it output this, and then we will drop down a scene animate node. Scene animate, and then go to the animate state. So we want to simulate this Electra test geometry inside this Apex animate state by creating a solver for this in the Apex graph. But before we do that, we want to see that how we can control our simulation inside the Apex animate state. So as you can see, for example, if we take a look at this this cogwheel controls, we have a lot of configuration options, and we want a similar one for our solver, so that we can configure that how and when our solver starts and how and at which time it stops, and also some other kinds of solver parameters if you want to promote that. So we will learn to do that in a Apex graph node. And after the Houdini 21, we go out of the Apex animate state for a minute. After the Houdini 21 version, this Apex graph node has changed, and now if you don't have any input for this, which contains a Apex graph, it will automatically create it for you and edit in a packed folder, and then you can go to the animate state and quickly test it out. So now we will see that how we can create an control for our solver, so that we can later use it for our custom solver. Now let's go to a Apex network view pane. You can open it by clicking on this plus icon and new pane tab type and animations and Apex network view, and then over here we will create a input and an output, so that our base.rig works, and then we get some the controls working in the animate state. So now we want to, for example, we have let's take a null, and for example we want some value from it. So for example, null float, and we want this value to be inputted to this null. And in this place you can think of our solver, which we are later going to create. So we want to find a way so that we can get some values from the Apex animate state and use that for our solver's parameters. For example, it can be the sim time, the simulation time. So to do that, we will use the node called rig abstract control, and this abstract control has many purposes. For example, if you promote the x and y controls of it, then you will see that if we go to the animate state, you will see that the graph is working as I said, It automatically adds it in a packed folder, and now we can go to the animate state and pose. So you can see that we have this rig abstract control 1, which is similar to the name we give it over here. For example, if we change it to test, then it will change it over here too. As you can see, it is test now. And the x coordinate and the y coordinate which we promoted here can be controlled from this apex animate state. For example, if you select this and drag it, then you will see that it gives you a nice HUD which you can use to control the x and y coordinates using your mouse in the screen space. But what you can also do using this abstract control is that you can promote and take some other kind of value, for example a vector or a float or a string. And to do that, you have to use this pair inputs of this abstract control. For example, we want to take this sim time input for this null, which will later be our template solver. So we want to take the sim time for it. Then we can connect it obviously to this pair input. This pair input, you have to just connect it and it will automatically give it the name too. And then you have to promote it to this input node. And then if you go to this animate state, you will see that we still have this. And if you click on it, you can do nothing. I mean, you can't drag it right now to change the value. But if you press G to get the parameter HUD, which is used to control the parameters, you can see that we get this sim time parameter. And then we can use it however we want. For example, we can set it to 2 or anything we want. And we can also animate it, for example, if we set some keyframes by holding Alt and clicking on it, but we are not in a Apex Scene Animate node, so we can't store any animated channels. But we will be able to do that when we do it for this Electra character, and then we use a scene animate to animate it. And you can also offset this abstract control from this position. For example, if we use a transform build, which constructs a transformation matrix using a set of vector parameters, for example the transformation and the rotation and the scale and all of the other things, and it gives a matrix which you can use for this xform input, which sets the position of this abstract control. For example, we can set the translation to on the y-axis to 1, and then it will be moved to in the y-axis by 1. And you can similarly promote many more parameters, and you can use them in the parameter HUD like this by pressing G and getting this parameter HUD. So now, since we know that how we can control our solver from the animate state, we'll now build a prototype of our solver in the DOP network. So to do that, we'll add a DOP network in our geometry network, and we'll use this network to prototype our solver. And the reason behind why we are doing this, you can also create objects and data and relationships inside the Apex graph using the sim nodes, but we are doing it here because doing it inside the Apex graph is takes too much of work and it is not necessary. So we want to solve it using a pop solver. So we'll first drop down a pop object, and then we'll drop down a pop solver, and then we'll also add a ground object so that it has something to collide with, and then we'll create a relationship between these using a merge node. So a relationship between the ground object and the pop object using the collide relationship, and we'll make the ground plane a factor by keeping it on the left side. So left input affects right input, and you will also see it in the effector matrix. If we set it on frame 1, you'll see that the ground plane affects the pop object, and we'll also change this object name to for example particle obj, and we'll change this ground plane object name to ground. I hope this is set to $OS. Yes, object name is set on $OS. And now you can see that we have this ground plane. We'll not display the proxy geometry of this ground plane. And now we want to test our simulation using by getting the initial geometry over here. So for example, we can take this Electra geometry and do a unpack folder, and we want to unpack this shape. If we see it, if you click on this test geometry Electra node and go to directory, we have these three components in our packed folder: the rig, the shape, and the skeleton. And we want to extract the shape, so we'll say anything with the dot shape extension, we want to extract that. This is what this says. And then we will add a null. This will be our geo, and then we'll use it as a test geometry for this initial geometry parameter. So set it on test geo, and now as you can see, the geometry is imported, and it is in the geometry subdata of this particle object. So if you see it over here, as you can see, we have this geometry data, and it is set to this Electra geometry, and that's what this pop object does. If you double click on it, it attaches the geometry data and the physical parameter data and the, for example, the guide data and many things like that. But currently we don't have any force, so it doesn't do anything. So we'll also create a gravity for right now, but we won't keep it. We want to create it inside the apex graph, but we'll do it just for testing so that we know that what we want to achieve. As you can see, this is what it does. It treats the Electra geometry as a particle, and I think it will be better to use a wind force. I think it will be better. So a wind force, and we'll set the scale force to something like 2. And as you can see, I think it looks much better, at least. So this is the simple simulation which we want to recreate in the apex graph, but we won't create the wind force data over here. We'll create it in the apex graph. But what I want you to see that if we go to the geometry spreadsheet and take a look at the forces subdata of our particle object, it is here, forces, and it creates two type of data, this uniform force and the drag force. So I think that a gravity node will be much better example because it creates a single data. So let's use this and delete this. So it creates this gravity data, and as you can see, we have this gravity subdata over here. As we set it over here, we can turn off unique data name so that it is only gravity. So what I want you to see that all of the data which you set on the DOP network node, which adds a data to your object, all of the parameters of that node are a option. So if you take a look at the options of this gravity data, you will see that we also have the force data over here and over here too, and we also have this sampling mode over here too, which is a enumerator, and which we also have this handle pause, which is controlled in the viewport and not in the parameter window. But I just want to show you that everything which you control in the a node of DOP network which adds a data into the pop object. All of their simple data are stored in a option if it can be stored in that. For example, a float or a int or a vector or a matrix, all of that is stored as a option. So we will be able to create and modify these options in the Apex Graph 2 using the dictionaries. So I just wanted to show you this. So we'll delete this gravity node now, and now we want to output this DOP network which we created, which adds and applies some data, which adds some objects such as this ground plane and the pop object, and also adds this pop solver data to it, and also create this merge relationship, I mean the collide relationship between the ground and the pop solver. So we want to output it as a simulation file so that we can use it inside our Apex graph. So to do that, we'll use our output node. And as you can see, we have these options to output which are similar to a file cache node, which are used to output our simulation data, which is not just a geometry. It will export everything which you have over here, such as the objects and the relationships and the subdata. And to do that, first we will reset this parameter, this start in frames. We only want to export the first frame, so we'll set it on 1, and then we will turn off this output every sim frame using $SF, and we'll initialize the simulation operators so that it doesn't use any cache information from the disk. And now you save all of the simulation data files using this .sim extension, as you can see over here. So we can store it in our HIP folder inside the sim folder, which it will create, and then we can name it. So we can give it a name such as the pop solve object with ground. That will be nice. And then we want to save to disk, and now it is on the disk, and it is saved in a binary format, so you can't change it in the file after exporting, but you can re-export if you want from here, if you are adding any other data or any other objects or anything like that. So now our prototype sim file is ready, and now we'll see that how we can create a solver in the Apex graph. But before I do that, I will show you that our sim file is correctly stored. So to visualize that, we'll use a file node, a file DOP node, and and what this file node can do, it can also catch the simulation just like we did with this output node, but it can also read that. So we'll set the operation mode of this to read files, and then we will set the file name to the file which we saved, and then we will set the output flag on this. And if we reset, you'll see that we get this back. All of our objects and relationships and data, they are all saved correctly. So now we'll use this sim file as a prototype, and then we'll also create a gravity subdata to it in the Apex graph node so that our solver starts working. So let's go to the geometry network, and let's rename this DOP network to prototype pop solver, and then we will also rename this graph to build solver. And this is the Apex graph where we will now build our solver inside, and then we'll use that for this Electra's rig later. But before that, we'll build it in this Apex graph node. So if we go to the Apex network view, we can delete all of these nodes which we created for just testing. Now over here we will create a null geometry which will be the holder of our geometry, and now we'll collapse it in a subnet, and this subnet will represent our solver, so we can rename this as pop solver. And now we can jump inside it. We can promote this geometry, our null geometry, and first rename it, and then rename it as the particle geometry, for example, the geometry which we want to solve. And now we want to see that how we can create our solver, and we will do that using the sim namespace node, which is called sim engine. And this sim engine node creates a simulation engine which will be used later by the sim evaluate at time node. Now you must be wondering that what a simulation engine is, and a simulation engine is the owner of all of the data which you can create in a DOP network. For example, objects or data or anything like that, it lives under this simulation engine. For example, when you create a simulation prototype inside a DOP network, for example, just like we are doing it over here. For example, when we create a object or a subdata called solver, or create any relationship, all of that is owned and governed by a simulation engine. And when you are doing it inside a DOP network like this, that simulation engine is governed by this node. But you can also use a simulation engine inside this Apex graph, which will be free from this DOP network node, but you can still add some, for example, any kind of data or object or relationship to it. So this is the engine which we will use to add our load our simulation file, and then this engine will contain all of those objects and data and relationships, and then we'll evaluate any kind of data using this evaluate at time node. But currently it only supports evaluating geometries, so you can specify it in this data path, and it will be outputted by this geometry output. So right now we'll connect this engine to this sim evaluate at time node, and now we will talk about this evaluate at time node later. What we want to talk about is this sim engine node. So as you can see, it has two inputs. First one is the graph input, and the second one is the time step input. The time step input is for setting the time scale of the simulation. For example, we can set it to 0.004 or something like that, or we can promote it outside so that we can control it outside using a float value. And it has this graph input, and you can use this graph input which expects a apex graph handler, and you can create another graph inside a apex graph using the graph template node. And if we connected this graph to this graph input, and if we double click to go inside this graph template, you have one another graph over here, and over there you can modify the simulation engine, because it will run for every simulation frame of this the simulation when you evaluate it, and you can modify the engine the simulation engine easily over there. So to do that, we will go inside this graph template node, and we'll drop down a input node and an output node. This automatically gives you two inputs. First one is the a float which is called the sim time, which is what we pass over here. So if that force reset sim is on, then it will run from the 0th second or the time to the sim time which you provided. which we are going to talk about later, but that's something you should know. So this will be our sim time, and it also gives you the simulation engine as a engine. So we can drop down a null for that. We don't have a special null type for sim engine yet, so we'll use a spare input of this normal null so that we can later connect a simulation engine to it. So we will rename it to engine in small case, and this shouldn't have any typing errors. And you should know that because then you won't get the input correctly. And it also expects you to modify send the modified engine using this output node. So we can rename this to engine, and then we can output that, and that will be our modified simulation engine. So now this graph template which we created, it will, as I said, run for each and every frame just like a solver. I think that's how it is implemented as a solver. I think that's how it is created. So it will run like a solver, and it will modify our engine and we can add objects and datas and anything using the other uh, sim namespace nodes over here. For example, sim create object, you have the sim create subdata, and you also have the sim create object node over here, which expects a engine input, which we have over here. And now as you can see, it will automatically cast to the sim engine type. So you can create any object like this, and then you can create a sim create subdata, and then for example you can use this object as a root data and then add a subdata to it, for example a geometry or anything which you want. But that would be very lengthy to create it like that. So what we also have is a sim load from load sim file, which will load the simulation file from a .sim file which you have saved in the disk, and it will load all the objects and relationships and subdata inside it. So before we do that, what we want to do is we want to only do this for the first frame or the 0 time. So we'll do that using a if block, and for that if block we also need a boolean expression which will let the if block know that if it has to run or not. We want to use a node called equals which uses floats, and then we want to check if this sim time, which we will pass as the a input of this, is equal to this b input, which we can leave to 0. And by 0 we mean the 0th second or the starting frame. And then we will use a if block. So if begin and if end. Let's make some space over here. So we can connect the scope, and as I said, it needs a condition, a boolean condition, to know that if it has to run or not. And this if block, it will only run when we pass this condition is true. And if you don't already know about a boolean result, it contains either true or false, either 0 or 1. 1 means true, and then it will run, and if it is false, then it will not run. And we can also pass some spare inputs to this if begin so that we can use it inside it. So now in this if block, which will only run for the first frame, we can load the sim file. So we can connect the engine input of this sim load file, and we have to set the file name, which we can copy from this DOP network. So we can pin this Apex network view using this. so that it doesn't move when we move in the network. And then on the output node, we want to copy this path, and then we want to paste it over here. And now it will load that sim file and add all of its contents in the engine. And then it is the task of the simulation engine to find any data type which are of type sim solver and which have the data name of solver, so that let them solve the object for the other times which is not the starting frame. So now, as you remember, or you can see it over here, that we didn't add any gravity node, so we have to add the gravity data manually over here. And to do that, we will use the sim create subdata, and we'll find the particle object from this simulation engine, and then we will add this gravity subdata to it. So to do that, we will first move it, and then we will use a sim fin object which fins an object from this simulation engine using using the object name. So we can copy the object name from here and paste it over here, particle object, and then that will be the root data in which we want to create this subdata. And we'll give it the engine, and the data name should be gravity, and the data type we can copy it from this. So for example, we can create a gravity force over here just for reference, and then as you can see, we have to add it inside the forces subdata and not directly, so we'll do that also. And you will see that we have this forces and the gravity and the data type. This is what you have to enter in this in that data type option. So it is sim force gravity. See, so we will remember this and put this over here, sim force gravity, and make sure that you don't add any typing errors or your gravity will not work. And as I said, it also has to be inside this forces subdata. So we will add this over here so that it is under the forces subdata. But what we also have to do is set the parameters for this. And as I said, if you can, the parameters are stored as an option, and we can set them using the dictionaries. So we will use a null of dictionary as a template to add our parameters to a dict build node to build this dict dictionary. So first we want to add the this force, and we can leave the others on their default. So we can add a a null vector 3, which contains a vector of 3 component data, and we can pass that as the force. Remember that the option name should be matching to this so that it works. And then we will set it to this value, minus 9.8 on the y-axis. And then you have to provide it as this palms input of this sim create subdata to set up the parameters. And now in the simulation engine, this particle object has this gravity data attached. But what you must also remember that we also have to set the geometry subdata of this particle object so that it has something to solve. But I think we left the initial geometry turned on, so let's remove this geometry data from it, and then we have to output it again without the gravity node because we are creating it over there, and we can save to disk. And now we have nothing in the geometry data. If we take a look at the geometry spreadsheet, the geometry data has nothing inside it, as you can see. So before we set it, we have to get it from this input. And to get it in the input, we have to provide it inside this sim evaluated time palms input. So we will do that later, but we can take it already using a null geometry, and this will be our simulation geometry, and we'll name it PGO for particle geo, and that will be the name of the dictionary parameter which we will give later to the sim evaluated time, but you don't have to worry about it right now. We can pass this as a spare parameter too. We have already found this object, this particle object from our engine, so we just have to modify its geometry subdata, and to do that we'll use the sim set geometry node, which takes the engine as an input and the root data, which is the root of the geometry data which you want to modify, and the data name, which will be geometry. You can check it from the geometry spreadsheet over here. It is geometry, and then we have to provide this geometry over here. So that will be the spare input which we get over here, the PGO. And now we also have the geometry set it up, so we can give it a space, and then we can connect the engine as an output spare parameter, and then we can connect it to as an output of this. So this will be our simulation setup. We'll check if this graph is being called at the first frame, and if it is being called at the first frame, which means that our sim time should equal to 0, then it will load the sim file from this file. Then it will find the object, this particle object, which we create over here, which is in the sim file, and then it will create a sim force gravity subdata in the forces subdata, and it will also set the geometry so that it can solve it. Then later that solver which we have over here, this pop solver as a solver data, which also have the solver name. As you can see in this geometry spreadsheet, it is named solver. So then it will be later picked up by the engine, and for the later times it will be solved without any issue. So now we want to set up this evaluate it time node by giving it this input, which we this extra input. These two, sim time and the engine input, are automatically given by the sim evaluated time, but this PGO input is the extra input which we added, so we have to provide it as a parameter, this dictionary parameter over here. So we'll use a null dictionary as a template dictionary to add our dictionary elements to. Then we'll use a dict build, and then we'll pass this template dict, and then we'll add this geometry which we have over here, this particle geometry which we are taking from this subnetwork input, and we want to add it as an this variadic argument, and we have to carefully rename this to PGO, and you must check that it is if it is similar to this what you have typed over here. If it is not similar, then it will not work, and then we can provide this as a parameter. Now we want to talk about this sim evaluated time node, which evaluates your simulation engine at a given simulation time. So we want to promote this sim time as an output, an input of this subnetwork. And then we also want to turn on this force reset simulation, which what it will do that. For example, if this node is called for a sim time of 2 seconds, then if this force reset sim is not turned on, then it will try to directly solve it for the 2 second, and it will ignore any previous time. So if you so because we are doing our simulation file loading and all the other stuffs inside this if condition, which checks if we are on the start frame. If we want it to work properly, we want to turn on this force reset simulation. And then one another parameter which is it has is this data path, which is used to provide what kind of data which you want this sim evaluated time to evaluate to. Currently, it can only evaluate a geometry subdata. So we want to evaluate this geometry subdata of this particle object and not the ground object. You must remember this. So what we want to do is we want to copy this particle object name, and then we want to paste it over here, and then do a slash, and then we want to say geometry. That's what we want to evaluate. Particle object slash geometry. And then we can output it as a solved geometry. And this is it. So this is the basic solver setup. And now our solver is ready to work. So we can go outside and copy this pop solver so we can merge it inside this test geometry Electra's rig geometry. So now we can go to the scene view, and over here we'll use a apex graph node to edit the rig of the test geometry Electra. As you can see in the rig tree, we have this base.rig which contains the apex graph rig for this Electra, and that's what we want to get over here on this graph node. The graph path will be anything but with .rig extension, and then it will fetch the rig for you. And you can go to the apex network view again and turn off this pin mode so that it is not pinned to our this build solver graph. We'll unpin it from here, and now we have this graph, and we will press L to lay out this, and we'll bring this output the input node, this palms input node, which has a lot of nodes. So you don't have to worry about all of that which is happening over here. You just have to worry about this the input and the bond deformed geometry node. So we want to paste our solver over here, this pop solver subnetwork, and then we want to simulate this bond deformed geometry. So we can set up this this particle geo input to this bone deformations output, and then we can set the time step of it manually by setting it to something like 0.04, and the sim time we want to control it using an abstract control, as I said told you before. So we'll create a rig abstract control. We want to add this sim time as an spray input of this, and then we want to promote it to this input node so that we can use it in the animate state. So with this setup, we want to set this solve geo as the base.shape output, and now we are ready to use it in the apex animate state. But before we do that, we want to save this modified graph inside this test geometry Electra's packed folder. So to do that, we will use a packed folder node, and we will connect the Electra main geometry to this first input of this pack folder. We'll delete these scene animates, all of that, and go out of this animate state. Let's delete also this, and we will add this modified graph as the second input of this pack folder, and we will pack it as a base.rig, and now it will override the default rig the Electra has. So since we added the pop solver after the bond deformation is happened, we'll be able to do any kind of transformation on the bones, and then we will be able to solve it. So to use it, we'll drop down a scene animate node, and then we can jump to the animate state. And as you can see, by default our sim time is set to 0, and that's why no deformations are happening on the Electra. But it is a good sign that you are seeing this geometry, and that means that our geometry is being evaluated correctly, and even at the 0th time it is being evaluated properly. Now you can do any kind of transformation to it, example like this, and then we can press G to bring the parameter for this abstract control, and then we want to select this, and then we want to animate the sim time. So for example, we want the simulation to start from the 24th frame, and we want it to go from 24th frame to the 96th frame, and over here we will set it to 3. And remember that I am using alt clicking on it to make it work. And as you can see, this is working. The Electra geometry falls, and it exactly does what it did in the DOP network prototype. As you can see, it jumps off in the ground, and you can also pose it right now. As you can see, can pose it right now, and the solver will re-evaluate, and it looks really cool. So this is how you do it. You already have a nice solver, and it is working properly, and that's how you build other solvers inside the Apex graph. And one thing I want to tell you before we leave, that you can also mimic the way a SOP solver works inside these solvers. So for example, if we go to the network view, and inside our pop solver, if we go to this graph template, as I said before, it runs for all of the simulation frames or simulation time. So if you go inside it, and if we print the pop object over here, sim print object, and then we can go inside this top network while pinning it, so that we can copy this so that we don't make any typing errors, and then we can fin it from this engine, and then we can use a sim get geometry, and then a sim set geometry, and then we will connect the root data input of this sim get geometry to this object. We want to fetch the geometry from this object, and then we will set the data name to geometry. Make sure you make no typos, and connect the engine input. And then for this sim set geometry, the root data will be this object 2. We'll use the same engine, and then we want to use the same data name, which is geometry. And now between this geometry input and the output, you can use any for example, the SOP namespace nodes, which are the SOP verbs. You can use them to mimic the way a SOP solver works over here, for example, in the DOP network, where you have this input geometry and an output geometry, and you just iterate through it for all of the time. You can do the same over here between this sim set get geometry and set geometry block. So for example, we can do a geo transform and we can connect this geometry to it, and then we can use a transform build, and as I said, it makes a transform matrix using these parameters. We can translate it or scale it on the, for example, on all of these axes by 1.113, and then we will set it as an output geometry. And now it will work just like a SOP solver and iterate through it for all of the time. And we forgot to set it as an output engine of the our graph, so that's why it was not working. And now you will quickly see this working. Now if we select this, so as you can see, it will quickly change its size, and as you can see, it becomes very huge. So as I said before, you can mimic how a sim solver works using this method. And before we leave, please like and subscribe if you like this tutorial. Thanks for watching.